In this section, we'll learn how to use properties of definite integrals to evaluate definite integrals. We'll continue to use geometry when necessary. Again, in section 5.4, we will learn the fundamental theorem of calculus, which will aid our evaluation. So the first property of definite integrals is that if we evaluate a definite integral from a to a, we have 0. Now, you can think of this conceptually. Imagine that you have a function and you're looking at an integral from a to a. So here's our function f, and we're going to evaluate from a to a. What's the area underneath the curve at that point? Well, that might be a little bit difficult to see yet. So let's look at from a to b. And if we, again, look at this area, we have the definite integral from a to b. But now imagine we start to decrease the width of this rectangle, or the width of this region. In so doing, this area gets smaller and smaller because the region is getting smaller and smaller. So intuitively, it makes sense that this area is 0. Now also, if we change the order of integration and we go from b to a instead of a to b, then that's okay, but the integral from b to a will then yield a negative whenever we change the order of integration. Now, another important property is that if we have an integrable function on an interval from a to b, and c is somewhere in the middle, then we can break up our integral as two separate integrals. So if you think of this conceptually as an area, then if I think of region 1 and region 2, it makes sense that if I add those two areas together, I get the total area from a to b. And that's all we're saying here. Now again, this is overly simplified because definite integrals don't always correspond to area. But area is a nice place where we can get an intuitive grasp of what's going on. Okay, and now we have two more properties. And if we have a constant factor inside our definite integral, the constant factor can be brought out. Likewise, here we have a sum or a difference of two functions that we're integrating, and we can just split up those two functions and integrate each of them. This should actually be g of x, not f of x. My apologies. So let's use these properties to determine the definite integral's value. So here we have the integral from -3 to -1 of f of x dx. So let's take a look at the graph. If we look at the limits of integration, we have x equals -3 and x equals -1. Our function is non-negative on this interval, so therefore we're looking at the area under the curve, between the curve and the x-axis, that is, between -3 and -1. Well, that's just a rectangle. So therefore, we can use geometry yet again to evaluate. So this is 2 units. This is 2 units. So we actually have a square. And so we have an area of 2 times 2, which is 4. Now if we look at the integral from -3 to 1, we're looking now at this region. Now, we've already found part of this area, part of this definite integral, that is, from -3 to -1. So we can actually, rather than using a trapezoidal formula, we can break this up into the region that we've already found and then the triangle. So we can go ahead and say this is the integral from -3 to -1 f of x dx plus the integral from -1 to 1 of f of x dx. Well, the first integral is something that we've evaluated in the previous example. It's 4. But now the second integral corresponds to the area of the triangle. So this is 2 units. This is 2 units. And so the area of a triangle is 1/2 the base times the height. And so whenever we evaluate this, we obtain 6. So now let's look at the integral from 1 to 4 of f of x dx. So if I look at x equals 1 and x equals 4, this is a tad bit different than what we were used to. This time, whenever we go ahead and find this area, the region falls below the x-axis. So whenever the region falls below the x-axis, then we can think of the definite integral as an accumulation of signed areas. In other words, if I just look at the area of this, the area is going to be 1/2 the base, and the base is 3 units. And the height is 3. So the area of this triangle is 9/2. Now, whenever a region falls below the x-axis, then the definite integral does not correspond to the area. It corresponds to the opposite of the area. In other words, the area is 9/2. So the region's area is 9/2, but the definite integral is going to be -9/2. You can almost think of it as though if I draw a representative rectangle, that rectangle has a negative height. And so you can think of -9/2 as a signed area. It's not a true area in the traditional sense, so we won't call it an area. But we can use an area to evaluate our definite integral. Now we can put it all together because we are looking at the definite integral of this same function from x equals -3 to x equals +4. But we found this area in 2 pieces so far. So we found this area, and then we found this region. So I would break up my definite integral into those 2 regions. So this integral I would write as the integral from -3 to 1 of f of x dx. And then I would add to that the integral from 1 to 4 of f of x dx. Now I'm not going to go through and do all that again because I know from the previous examples that this first area, this first definite integral is 6, And then the second definite integral is negative 9/2. So if we put it together, we obtain 3/2. Now, this 3/2 does not relate to an area of these two regions in the traditional sense. But if we think about signed area, then this region has an area of 6. This region has an area of 9/2, but since it's below the x-axis, the definite integral would be a negative value. And now we can think of integrals as accumulation of area. And so therefore, if we look at this function as it goes from -3 to 4, it accumulates an area of 6 plus negative 9/2, and we obtain 3/2. So it's not an area in the truest sense. It's an accumulation of signed areas, as it were. At least that's a good way to think about it for now, until we see how definite integrals can be expanded to look at different types of quantities. An important thing, though, is to remember that definite integrals do not always correspond to an area. We'll see where in later sections they can correspond to volume, they can correspond to arc length, they can correspond to surface area. And so this is a tool for your toolbox, and we're just seeing one of the uses now.